Okay, welcome back to EE 210B. We are going to continue our discussions of strategies for adaptation, learning, and optimization over networks. So in the last two lectures, I introduced the network model. Right? You all know what a connected network is, what a strongly connected network is. In the last lecture, I introduced the global optimization problem that we would like to solve over these networks. We would like to minimize the sum of individual cost functions, and then I described three classes of strategies to help with that objective, right? Incremental strategies, consensus strategies, and diffusion strategies. Remember that? And I also spent some time talking about the traditional consensus, the original consensus idea, right? Now, in this lecture and in the next 2 or 3 lectures, we are going to go deeper into analyzing the performance of these networks, how well they learn, how fast they learn, okay? And as you are going to see, that will take some effort. More effort than when you study standalone agents like we did in the earlier lectures of this course, or when you study the centralized solution like we also did in an earlier lecture in this course. And the main problem that we are going to encounter now is that because you have a network, you have coupling among the agents. What happens that one agent affects the performance of other agents, right? Different agents will have different noise conditions. They will be measuring data under different noise conditions. You also have a network, and this network may be sparse, may be dense, so the topology has an influence, right? So all these issues will come up, and these are issues that we did not have in the single agent case, maybe, okay? Very good. So the material for this particular lecture comes from chapter 8 in the text that I indicated to you earlier in this course, okay? So this is what I'm saying here, that now we are going to start to analyze the behavior and the performance of the strategies that I introduced to you before, okay? This analysis will start mainly from the next lecture onwards, okay? Today I'll still spend some time trying to understand the network and trying to understand what the strategies will be performing over the networks. But then, starting from the next lecture and the lecture after that, we're going to go deeper and establish many of the statements that I will be making along the way, okay? So like I said, answering questions about performance and behavior is more challenging than in the single agent case and in the centralized case for 2 main reasons, right? First, now you have coupling between agents, and second, now you have a topology, and that topology may be sparse or it may be more fully connected, right? So these are issues that come up now, okay? Nevertheless, we are going to develop results and theorems, right, and prove properties that will allow you at the end of the day to look at a network and be able to tell, for this particular topology, this is the kind of performance I can expect. This is how fast it will converge, and this is how close it will get to the optimal solution I'm looking for. And you'll be able to compare different topologies against each other. You'll be able to tell whether this network, or how much difference you will get in performance between different network topologies. You'll also learn how to make topologies behave similarly, for example, even though the graphs are different, okay? So these are questions that you'll learn how to answer once we are done with the analysis, okay? Very good. So before I get into that, okay, which we are going to start establishing starting from the next lecture, I want to prepare you for the kind of derivations, for the kind of analysis and techniques that we need to employ, okay? So to introduce that, I will start with the simple case of mean square error networks. If you remember, these are networks. They are strongly connected networks. Each agent is receiving a reference sequence D and a regression sequence U, right? So let's go, okay? So you have a network, right? And you may have a topology over that network, right? Okay, each agent is receiving dk of I and a regression vector uki. I'm going to be showing you the example, right? And each agent has a cost function associated with it, which is the mean square error cost, right? the expected value of dk minus uw squared. Okay, I will be showing you the details in the next few slides. So let's start with this particular network and examine how the errors evolve over time. The kind of analysis I will be doing for this network will be repeated many times in future lectures. So I would like to show you how the analysis is done in this simpler case, so that it will be much easier for you to follow the analysis in the more general case. You understand? Technically, I don't need to do this. I can go directly to the general case, but I want you first to see it in the simpler case, and then you will be able to appreciate the more general case, okay? So this is the situation. I have a network with n agents, okay? Each agent is measuring reference data d sub k and regression data u sub k. This is a scalar. This is a row vector. They are generated from a model WO, which you don't know, you would like to estimate, and v sub k is measurement noise, right? And we assume the noises are independent across agents, and over time, the regression vectors are independent across agents, and they are also white over time. And noise and the regression data are independent of each other, right? These are the standard assumptions we introduced for this particular problem, okay? And this is the covariance matrix of the regression data, and we also defined, by the way, the cross covariance or cross correlation between d and u, which is the expected value of dk of I, uki, right? Remember, we have these two quantities here. Okay. Now, with each agent, we associate this cost function, which is the mean square error cost function. And if you were to minimize this individual cost on your own, we already know what the solution is, right? The solution is given by the solution to the normal equations, right? RU inverse RDU, right? So I'm assuming the RU is invertible for now, okay? You all understand this? Okay. So this is the solution to this problem, the minimizer to that cost. It's given by this quantity. And if you go back to the model here, if you multiply from the left by U star, U star, U star, and you take expectations, so this last term gives you 0 because they are uncorrelated and V is 0 mean. Here you get RDU K is equal to RUK W0. So you see that the W0 that you want satisfies the same normal equations as the one that's satisfied by the minimum of this cost, right? So this is an example where all individual costs, even though the RDUK and the RUK vary across K, but all of them will give you the same minimum for all individual costs. This is not the case generally. In general, the individual costs at the different agents need not have the same minimum. For the case of the mean square error network, they all happen to have the same minimum omega 0, right? Understand? Because we are going to see later when the minima are not the same, some additional terms will appear in the evolution of the aerodynamics that we do not see, that we will not see in this example, okay? Very good. So now, remember again that the Hessian matrix in this case, your cost function is quadratic, right? So if you differentiate it twice relative to omega, you are going to get the covariance matrix. But because we are allowing for the weight vector to be complex, right, like I explained in the earlier lectures of this course, how do you differentiate relative to a complex argument? The second order derivative, which is the Hessian matrix, will be twice as big, 2m by 2m, right? In the real case, it's just m by m. But in the complex case, it will be 2m by 2m. It will be block diagonal, and it will have RU and the transpose of RU, right? Okay, so this is the derivative, this is the Hessian matrix of this quadratic cost here, relative to an argument omega, and we are allowing omega to be complex, as you see up here. Omega belongs to C, to Cm. Okay, so this is to accommodate general applications where the unknown may be a complex variable as well, right? Okay. Okay, so just remember this because this is another little detail that will not happen in the general case. The Hessian matrix in the general case need not be block diagonal. because it is block diagonal here, some simplifications happen here that will not happen in the general case, okay? So you already saw two simplifications in this case, common omega 0, common minimizer, and a block diagonal Hessian matrix. That's why when I talk about the general case, the arguments will be a little bit more involved, not much, but it's because of these differences, okay? So now if you continue, here I am summarizing the algorithms for you. Okay, what is the first algorithm? The first case is if each agent were to run an LMS recursion on its own, trying to estimate its own minimizer. That's the recursion, right? Agent K at time I is what the value is at time I minus 1. Step size, regression vector times the error, right? And this is run independent of any other information from any other agent. This is the non-cooperative case. If instead the agents now cooperate, they are connected by a topology and they want to cooperate, they can run, for example, one of these strategies, right? Consensus or diffusion. For example, in the consensus case, agent K will combine the estimates from its neighbors, right? Using some coefficients A that add up to 1, right? ALK that add up to 1. And then it uses that intermediate estimate as a starting point, but not necessarily to find the gradient vector, right? Like we explained last time. Okay? So this is the consensus LMS iteration. First, I see what my neighbors tell me the estimate should be. Then I start from there and move along the direction of this approximate gradient, right? And every other agent in the network is doing the same thing. In diffusion instead, you also combine the estimates of your neighbors. However, you use that information both as a starting point and also to evaluate the approximate gradient vector, right? It becomes more symmetric. And in the ATC version, adapt, then combine, you adapt first and then combine. Right? So you adapt to get the intermediate value and then you combine, right? These are the strategies that I described last time, specialized to the mean square error case, right? Here I have written before the approximate gradient vector. Now I'm writing what it is in the mean square error case, right? Very good. Now, if I would like to know how well these algorithms perform over a network, what do you need to do? You know, if you were to solve this problem, this is what you would need to do. You would like to know, as time evolves, how far the estimates, let's say, take any particular agent WKI, see how far it is from this W0 that you would like it to converge to, right? So you can define an error quantity, which would be this difference here, right? Call it the error. Right? Now, every agent in the network will have one such error, right? And they are not necessarily the same, okay? So if you collect all these errors from agent 1, agent 2, agent 3, agent n into a big vector, let's call it W tilde I. You see, there is no K now anymore. This is the network state vector, right? This is the state vector of the network at time I. Right? Each one of these arrows has size m. What would be the size of this W tilde I? Nm, right? It's a block vector. So whenever you study the evolution of networks, you will almost always be dealing with block quantities, block vectors, block matrices, okay? This is normal because of situations like this. You group. So now I would like to study the evolution of this W tilde, right? How it evolves over time and how close its entries get to omega 0, omega 0, omega 0, to 0, 0, 0, 0, 0, right, for the error. This is what we would like to do, okay? Now, I can do it for each one of these algorithms separately, right? I can do it for this, and then I can do it for this, okay, but that's not what we are going to do. Instead, I'm going to use a unified treatment. All these algorithms, I can view them as a special cases of one particular way of writing the algorithms, which I'm going to show you in the next slide. And then I use that particular form to study all of them uniformly. Okay, so let me describe this general form. Consider this general algorithm. This general algorithm includes these 3 steps. A combination step with coefficients I'm calling A1. okay, an update step with coefficients I'm calling A0 from some matrix capital A0, and a subsequent combination step with combinations I'm calling A2. Now, I claim all the algorithms I showed you in the previous slide are special cases of this. How? Let's look at it. Okay, so I have three matrices now, right? A1, A0, A2, right? We are all left stochastic matrices, meaning that the columns add up to 1. Okay, so these combinations here that node K uses to combine agents in its neighborhood, they add up to 1. Similarly here, right? Let's assume A1 is the identity matrix, A0 is the identity matrix, A2 is the identity matrix. Then only their diagonal elements are 1. Their off-diagonal elements will be 0. So if you come here to the first equation, only when L is equal to K, you will get 1, right? So you will get that phi K is simply WK, right? So forget about phi. Here you will get that this sum is simply phi K, which is WK, right? So this first term is simply WKI minus 1, WKI minus 1, and this psi is WKI, right? So all these three things become simply WKI, and on the right-hand side you had the LMS recursion. That's the non-cooperative case. Understood? Right? Okay, so let's take another example. Let's assume A1 is some left stochastic matrix A, and these continue to be I. So this is some A, right? So you combine, this is like a combination step. This is identity, right? So you will simply have here phi K, so this quantity comes here, phi Ki minus 1, phi Ki minus 1, and this is simply WKI because that's identity. So when this is A, this is I, this is I, this becomes combined and adapt, right? When this is I, this is I, this is A, this becomes adapt then combine. When this is I, this is I, this is A, it becomes consensus. You understand? So different choices, right? So this way, okay, I have a table here. So if I introduce these three matrices, okay, and I'm also, by the way, introducing their product because their product will turn out to be important, okay? So different choices, and I have them here. If all of them are identity, they collapse to the non-cooperative case, okay? For example, if two of them are identity, and the third is not, you get diffusion, right? And similarly for consensus, right? Okay, but you can have other options, by the way, and you will have a different algorithm. You can have other options, but these particular choices, fine, understood? So one thing I want you to observe is that for consensus and diffusion, two of the A's have to be identity, and the third A, whether it is the first, the second, or the third, has to be some A, left stochastic A, right? So P is simply that A because it's the product of the three A's, two of them are identity, so that P is simply that A. Only when you have multiple A's here that are not trivial, this P will be a product of A's. But in general, it is just that particular A. We will be dealing with consensus and diffusion most of the time, so that P will in general be that quantity, okay? So this is the general algorithm. I define the errors here because now you have two intermediate quantities and the last quantity, right? So let's define the errors. W0 minus this is an error, W0 minus that, right? These are the errors, okay. So if I define these errors, here it is, okay, I define the errors. And by the way, just so that you understand my notation, so here I write I, whereas here I write I minus 1. Okay, my notation is simply like this. I use I if the computation of a particular quantity requires data at time I, so that you know when that quantity becomes available. So you see, this quantity only is using data from time I minus 1. So I don't really need to wait until time I. I can compute it right away at time I minus 1. Whereas here, you need to wait for data that arrives at time I. So this quantity will only be available at time I, right? Technically, I could have called it psi k I minus 1, but I want the notation to be suggestive, okay? It doesn't only tell you where the variable is available in space, but also at what point in time you have it, okay? So that's why one of them has subscript I minus 1 and the other two have subscript I, okay? So these are the errors. Now, I can take these recursions and transform them into error recursions, right? You see, look here. If I subtract this minus that, this becomes phi tilde, right? Let me just do this slowly because then I can move through it quickly. This difference here on the left becomes this, correct? But I have to subtract there also, right? So you see, this quantity, I can also write it like this. Why? Because W0 is a constant. It doesn't change with L, right? So it becomes, this is like writing this, right? And that sum is 1, correct? So nothing changed, right? So I can write it this way, or I can write it this way. If I write it this way, I can group these two terms together, right? So it becomes, you end up with a sum, when you group them together, of A1 LK, W tilde, Li minus 1, correct? Right? Did you follow this derivation? So that's exactly where I got this first relation from. Similarly for the last one, if you subtract W0 from both sides, you get that relation. Similarly for the middle one, if you subtract, you get here psi tilde, and then you group them, you get this first term. And what about the last two? If you go back, okay, so when I subtract, you subtract here, so you can group these two terms together like I just explained. This becomes a minus because of this minus, right? And then here, and remember that D simply comes from the model, the regression model, right? Correct? This is D. So you can see here I have U star U, U star U, and then WO minus phi, right? So you will get U star U phi tilde, and then U star V, right? So that's where this last term came from, right? So it's easy to get an error recursion. So these equations are telling you how the errors evolve at location K, right? Over time. I'm not interested in that. I'm interested in knowing how they evolve across the entire network, right? So just take them and collect them into big vectors, and let's find the recursion for that big vector, okay? Because you can see here the error at any particular location in space depends on the errors at other locations in space, right? And they also depend on errors at other locations in space. So they are coupled, okay? Okay, so before I continue, let me just remind you of the gradient noise. Remember, what was the definition of the gradient noise? The gradient noise at agent K, right, is the true gradient, right, relative to omega at W star, right, minus the approximate gradient. Remember that? It is the approximate minus the true? Okay, so if it is reversed, let's reverse it. So the approximate minus the true gradient, right? Okay, so what is the true gradient? Remember that minus the true gradient in the quadratic case will be something like this. R duk minus RUK phi. That's what it is if you go, okay? And the approximate gradient in the LMS case is what? Is U K star dki. This is just from the LMS recursion, right? Right? This is the correction term that you multiply by mu. That's the approximate gradient. So if you subtract them, you get exactly this expression. Because remember, from the normal equations, this quantity here is RUK WO. So you can group these two things into RUK phi tilde, right? And then remember, this D is UWO plus V. So you will get U phi tilde and then U star times V, right? So I'm just showing you where this expression came from. It's trivial. You just subtract the two gradient from the old gradient, just because this will be useful for now. We don't need it, but I'm just reminding you, okay? Now, so if I come back to this recursion, I'm going to collect all these errors together into big vectors, right? So this is what I'm going to do. I'm going to define these network error vectors. You see all the W tildes from across all n agents, I collect them into a big vector. The same thing for the psi, the same thing for the phi. Correct? And I would like to know how this evolves over time, not the individual ones. I'm interested in the network dynamics, okay? I know how each individual one evolves over time. Likewise, I'm going to define these vectors. So let's look at what these vectors are. You see, this product, okay, I can, at every k, I can put them together into a big vector z, okay? That's what I did here. And I put the gradient noise into a big vector s, okay? Fine. So now, if you go back to your recursions, you will see the following, okay? Let's introduce, these are the combination matrices. Okay, let's introduce their chronicle versions. What are their chronicle versions? What is A0 chronicle I? You take every location of A and you multiply it by the identity, right? So let's say A00 becomes a diagonal A00, right? A01 similarly, right? So essentially you expand every entry into a diagonal. That's what these operations are doing. Okay, very good. So I call the expanded versions always calligraphic A. Okay, so again, my notation, whenever you see a calligraphic quantity, it is network related. It is related to the dynamics of the network. Okay, normal font, it is related to the dynamics at the local level. Okay, calligraphic at the network level. Okay, this is the notation. Okay. Similarly, I'm going to collect all the step sizes into a matrix M. mu1, and they are, again, multiplied by the identity. And I'm going to collect U star U. These are matrices, right? U is a row, U star is a column. So these are matrices. Where does this come from? If you go back, I don't only have the products of U stars with V, I also have the product of U stars with U. Okay? So these I collected into a vector Z. These I collect, because these are matrices, so I collected them into a block diagonal matrix, which I'm calling Ri, and these I collected them into a vector which I'm calling Z. Okay. Anyway, these are just definitions for now, okay, but they will repeat. So now if I go back to the recursions, you will find out that they can be written in terms of the network variables like this. Let me show you one of them at least, and then you will be convinced, okay? This recursion here, before, at the node level, it was like this. Phi tilde k, I minus 1, is the sum, A1, Lk, W tilde L, I minus 1. It was this, right? Okay, but now remember, my W tilde vector, this vector here, right, contains all the W tildes, the one at 1. Forget the I minus 1 for now. Let's just put the index where, okay, anyway, let me write it. My 1, 2, right? You keep going like this until this is what you have in this vector here, right? Okay, now I need to multiply by something to get the vector of phi tildes, okay? Phi tildes. So I will get phi tilde here, 1, I minus 1. Let's start with that one. What would that be? Phi tilde 1. Phi tilde 1, when k is 1, okay? You will have some neighbors, right, for that agent k. Let's say this neighbor, that neighbor, that neighbor, right? You will be combining, let's say, this W, that W, right? Because these are vectors of size m, these a's have to be multiplied by I, right? This is to match the dimensions, right? So this little a is multiplied by the identities, right? And then you combine the corresponding w's, that will give you the first phi tilde. And then you repeat for the second. For this. So you see that the vector of phi tilde will be this Kronecker extended A times the W tilde. You understand what I did? Where this came from? Okay, it's simple algebra for you to verify that this is the case, okay? That when you put them together, you have to use the extended A, okay? The same thing at the bottom, okay? What about the middle? The same thing. Because here, this A0 phi tilde came from the sum of A0 LK phi tilde L I minus 1. That will give you that term. The last one, MZI, look here. You see, this is mu. Put them together, so you will have the different mu's multiplying the vector Z, right? Then that gives you a column vector which contains all of these quantities, right? And then the last one is you'll get this matrix M of step sizes, diagonal matrix, times this block diagonal matrix R, times the vector phi tilde. It collects all of these together. You understand where they came from? Okay, so this is the network version, okay? Network version, okay? Network vectors. But now I'm not interested in the evolution of each individual error. I'm interested in the evolution of the ultimate error. Well, replace. I know this psi tilde is given by this expression. And it depends on phi tilde, which is given by this expression. So take this, put it here, right? And then take the entire thing and put it here. Then you will get a single recursion involving the W tilde. Okay? So when all is said and done, this is what you arrive at. This is what we were looking for, okay? This is what we were looking for. This is how the network dynamics evolves over time. Fine? The new error vector is some matrix times the old error vector plus some driving term. Remember, this Z contains U star and V, contains the the measurement noise in it, right? Measurement noise in it. This contains the step sizes, combination weights, step sizes. What was this R? Block diagonal U star U, right? If I did not have any cooperation, I can get that as a special case. If I set all the A's to the identity matrix, you see, I get this recursion, which tells me how the non-cooperative solution evolves over time. It's a special case of that. Okay? Did you follow up to this point? You followed? Okay. So there it is. Now for the general case, okay, in the general case when the cost functions do not have a common minimizer, we will get a very similar relation, but there will be an additional term. Number one. Number two, because the Hessian matrix will not be block diagonal, actually we will get two of these. This will not be enough. We will have to find a recursion for W tilde, and we will have to find a recursion for W tilde star transpose. We'll have to extend this vector to size 2m. You're going to see that. Okay? And these two recursions will be coupled by that Hessian matrix, which is not block diagonal. When the Hessian matrix becomes block diagonal, the two equations decouple, and you can live with only one of them, which is what we are seeing here. But in the general case, they will not be decoupled. Okay? So when we get there, you'll understand what I'm referring to. Okay? Very good. Okay? Now, this is just another way. So here, this is one recursion, one way of writing the recursion, involving here a coefficient matrix that changes with time, and involving the vector Z. But remember, I also defined the gradient noise. This gradient noise is defined here. It involves Z in it, elements of Z. So if I put this S together into a big vector, that big vector S will involve the big vector Z, right? And it will involve the big vector phi tilde, and it will involve a block diagonal matrix containing the RUs and the U star U, if you construct the big vectors, okay? So I can replace Z by S minus that. Right? So if you do this algebra, it gives you another equivalent form for the same recursion, which will be useful later. Here it is. This is the first recursion in terms of Z and Ri. But if you replace Z by what it is in terms of S, the recursion takes this form, useful form, where the driving matrix now is a constant. That Ri is not there anymore. It becomes a constant. It's replaced by R, the covariance matrices. So where did the Ri go? Well, remember that in the expression of Si, it had an Ri. That Ri ends up canceling the Ri here. So this form is useful because B is constant, and we'll be using it a lot later. Okay? You understand? These are two equivalent forms. Okay? Two equivalent forms. One uses Z, the other uses S. Okay, in the general case, we'll be using more this form, okay, because the B is a constant, and that's very useful, okay, as you are going to see. Fine? Yes? Is
it, in general, would be a constant or would be random variable?
No, in this particular case, it's a constant, you see.
But in other cases?
And we will be able to rewrite it in a form, as you are going to see, okay. We will have to massage it like I did it here and write it in a form that will involve a constant matrix, okay. You are going to see that probably in the next lecture, not today, okay? Okay. So continuing. So let's continue with this example a little bit, because this example already allows us to see some things that are interesting, okay? See, all I did so far is just algebra, plain algebra, right? I just did it slowly because this is the first time you see this kind of algebra, right, over networks. You just have to define the right extended quantities and put them together. But the algebra is straightforward if you do it, okay? Now, so let's take this is the first example. So let's take this example further. Let's look at the mean behavior. How does the mean of the error evolve over time? Okay? Well, if you come to this recursion, remember, gradient noise, remember the conditions we impose on gradient noise, right? Usually the conditions that, okay? That conditioned on the data, this gradient noise is zero mean, right? Is zero mean, okay? So, if you compute the expectation of both sides of this recursion, okay, this is what you are going to get. That term involving S is going to disappear. You understand what I'm saying? Okay? Because, you see, if you compute the expected value of W tilde based on all past omega, that's what this notation means, all previous estimates, you will get B, this, plus 0, because this condition on the past is zero mean, right? The gradient noise, like we described before, it will also be here in the network case, okay? I will be more explicit about this later, right? And then take the expectation again, you remove the conditioning, right? If you take the expectation again, then this disappears, and this becomes expected here, and this is the relation that you have here, correct? Yeah.
But the expectation of the gradient noise without the filtration, it's also zero, right?
Sorry?
You don't need the...
Yes, but this is, yes. But this argument, yes, that's true. We showed that, right? We showed that. Yeah, you can do that. I don't need to do that argument, actually. Yes, I can do it directly, right? Okay, because these are constants here. Okay, so expected value of this is B expected plus 0. Okay, good. Now, so, the mean evolves according to equation 28, correct? For a distributed algorithm. What was the expression for B? Remember? Okay, let's look at the expression for B. It involves the combination policies plus the step sizes plus the covariances, right? Okay. Now, in the special case when you are talking about the non-cooperative strategy, what would be B? Just that, right? Okay. In the diffusion case, what would be, let's say in ATC, what would be B? The first A will be identity. It will be A transpose I minus MR. In CTA, I minus MR, A on the other side, fine? And consensus, A transpose, because A2 and A1 will be identity, minus MR, right? I have these expressions written later. Very good. So now, I have just showed you that the error over the network evolves according to this first order recursion, correct? Correct? Okay. In the non-cooperative case, this is B. In the diffusion case, this is B, okay? Now, the interesting thing is, B here is block diagonal, right? Block diagonal, okay. Now, if you remember when I talked about or I reviewed matrix results for this course, right, one of the earliest lectures in this class, I proved, or I just stated a result like this, the proof of which is in the notes, that if I have a block diagonal matrix D, block diagonal, okay, Hermitian. It is Hermitian here because R is Hermitian. This is just a scalar, so this is Hermitian. Block diagonal Hermitian matrix. And you multiply it by any left stochastic matrix from the left and any right stochastic, you multiply it from the left and right by any left stochastic matrices, A1 and A2. One of them can be the identity, right? So this is what's happening here, right? Right? Left, identity, right, identity. We showed the following fundamental result, that the spectral radius of this never increases. It's always upper bounded. This is a matrix result. If you go back to the lemma, the proof is there. The spectral radius never increases. What does this mean? Very interesting here. It means if the step sizes for your non-cooperative solution are such that the dynamics is stable, this matrix is stable, this is your D, right? What can you say about the dynamics for diffusion? They will also be stable. So if your non-cooperative agents are stable, diffusion will always be stable, regardless of the A, regardless of how you connect them. Remember I made this remark earlier? This is a simple proof, okay? So if the non-cooperative agents are stable, diffusion will keep that stability. It doesn't destroy it. Actually, it may improve it because the spectral radius can be smaller than that, okay? The spectral radius is what determines the rate of convergence. If it gets smaller, it becomes faster, right? Okay. What about consensus? That's not necessarily the case anymore. Okay, this can be stable and this becomes unstable. Why? Because here it is multiplicative, but here it's additive. And you can come up with examples, I'll show you, where this is stable, but that becomes unstable. This is not guaranteed anymore for consensus, okay? Because of the asymmetry in the consensus update leads to an additive structure for B, to a multiplicative structure here. This multiplicative structure preserves the stability. The additive structure does not. You see where we are going, right? So this justifies some of the remarks I made before, okay? So this is what these examples are showing. So here, this is in general, this is the non-cooperative, right? Remember, the step size is here. You just choose a step size, okay, smaller than 2 over rho of RUK, because these are the diagonal blocks of this matrix, right? This is a block diagonal matrix. You choose each step size to make each block stable, right? So if the step sizes are like this, the non-cooperative agents are stable, right? Okay. And then, actually, I said more than I should for this example because it ends here, but you get the idea, okay? That's where this is going, okay? Actually, what I said is more general than this example, okay? In this example, I want to show you the same result in a way where you don't need the result of that lemma. This is a special case. This is more special than what I just showed. Let's assume that all the step sizes are equal. All the RUs are equal, okay? This is already subsumed by what I stated, okay? But I want to show it to you so that if you don't want to rely on that lemma, you will understand where this comes from. You see? So because the M is mu1I, mu2I, and so forth, and all the mu's are equal, right? So this now becomes this, right? Because you take each mu multiplied by I, right? And again, because all the RUs now are equal on the diagonal, it becomes this, right? So in this particular case, when you have uniform covariances, uniform step sizes, the matrices M and R end up with a Kronecker structure. Okay, very good. So now, you just come back here, replace M and R, and remember, A already has a Kronecker structure, right, by definition, right? So all these matrices now that appear here have Kronecker structure. So replace, right? Okay, then you will get these quantities. Okay, for example, just so that you see that this is indeed the case, let's establish one of them. For example, let's see, which one do I establish? Okay, this one. Let's show that this is the case. Okay, here. Remember, this is the definition of the coefficient matrix for diffusion, right? A transpose times that. Fine? Okay, so M here, Kronecker, R, Kronecker, right? MR, this is M, this is R. Now this I can be written as this Kronecker, and the A is that Kronecker. Fine so far? Okay. This mu, which is inside, I can take it out. Nothing changes here. Okay, that's all. Okay? And now, you see the product of this with that, you get I times I, Kronecker, R times I. Correct? That's the property of Kronecker products. Okay? Very good. And then here you can group these two terms together. They have the I, right? So here, I, Kronecker, IM minus mu RU. Again, properties of Kronecker products, right? Okay? And then again, now A transpose times I, Kronecker I times that, you get this quantity here, right? So you see, this is exactly what you have here. Okay? So in the uniform case, the expressions for the quantities become like this. Now here you can see the statements I just showed you before from first principles. You see, assume the what are the eigenvalues of this non-cooperative matrix? They are the eigenvalues of 1 minus mu r, right? Okay. Because the eigenvalues of this are 1, right? So, okay. What are the eigenvalues of the diffusion matrices? They are the product of the eigenvalues of A times the eigenvalues of this. But A is left stochastic. What's the spectral radius of a left stochastic matrix? Right, so the eigenvalues at most have magnitude 1. So you can see here that the magnitude, right, of this will never exceed the spectral radius of that. So if this is stable, the last two are always stable, regardless of A, right? Regardless of A. But this is not true for the consensus, because it is additive. Okay, and I can show you examples. You understand? Okay, so this is another way to see this. Okay? This is what I'm explaining here, okay? So the eigenvalue for the diffusion, I just showed you the product of this with that. For non-cooperative is that. And then some simple algebra will show you that the eigenvalues for consensus, you subtract, okay? This is not difficult to see, okay? Because here, this is the consensus matrix. I would like to find its eigenvalues. It's very easy for you to know what the eigenvalues of this and this is, right? From the properties of Kronecker products. It's less trivial for this, because there is no property I can use, right? But this is how you can find that the eigenvalues actually for this, they are related to the eigenvalues of A minus mu eigenvalues of RU. So how do you prove that, right? How do you prove that? Here, this is the proof. Okay? This is the proof, okay? So let's introduce eigenvectors, okay? Write eigenvectors for A transpose and RU. So A transpose xk is some lambda k of A, xk, and RU ym, lambda m of RU. Right? Just introduce these eigenvectors, fine? Very good. So now, let me show you that xk Kronecker ym is an eigenvector for the consensus matrix with eigenvalue given by the expression I showed you, lambda k of A minus mu lambda m of RU. If I show this, I would have shown that the eigenvalues of this matrix are indeed this combination, right? If I can show, I'm claiming here, right? I'm showing the next slide, that the Kronecker product of these two vectors is an eigenvector for the consensus coefficient matrix. With this eigenvalue, then I would have recognized what are the eigenvalues of the consensus matrix, okay? And this is the argument. So let's multiply the consensus matrix by that Kronecker product. Fine? Now here, A transpose Kronecker I times this Kronecker product, you get AX Kronecker Y. And here you get X Kronecker RUY. But X is an eigenvector for A, and Y is an eigenvector for R, correct? So I can take the constant eigenvalue of A out, eigenvalue of R out, right? And now this is a common factor here, which I take out, and you get the eigenvalue. Requires some algebra, right? Not from, okay? But the key point that this is additive. So if 1 minus mu lambda RU is stable, it doesn't necessarily follow. You can find examples easily that any A will give you lambda minus that also inside the unit circle. This is not true anymore. Okay? So this this is just repeating what I just said before, okay? That if the non-cooperative is stable, because the spectral radius of A is bounded by 1, is actually equal to 1, then the spectral radius of the diffusion matrix, right, in this example, will be equal to the spectral radius of the non-cooperative solution. If this is stable, that has to be stable, right? Okay. Not true for consensus. So if the individual agents are stable, mean stable, I mean diffusion is always mean stable, but if they are not stable, if the individual agents are stable, you cannot say the same thing about consensus networks, okay? Okay, this is just repeating the statement, okay? And this is a numerical example if you want to be convinced, okay? Here I just have two agents combining their weights. So 1 uses A and 1 minus A, adds up to 1. 2 uses B and 1 minus B, adds up to 1. Okay? Let's choose RU to be a multiple of the identity, RU2 a multiple of the identity, just so that we can do the calculations in closed form. Okay? So here, I'm going to choose the step sizes to satisfy these conditions. You see, mu is less than 2 over the sigma u, mu2 is less than 2 over the sigma u, so the individual LMS filters are mean stable. Okay? Then we already know, no matter how I choose A and B, as long, of course, as they are non-negative adding up to 1, we already know that if they run diffusion, they will always remain stable. Okay? But it's not true if they run consensus. There are values of A and B for which stability will not be satisfied, and you can find that, okay? Some algebra, I have this in the notes. This is the B for diffusion, this is the B for consensus. You can verify this is always stable no matter what A and B is. This is a simple algebra. Whereas, for values of A and B larger than this quantity, this will be unstable. You can show that, okay? And this is a simulation, one particular simulation to show you that this indeed happens. The individual agents are stable, diffusion will be stable, but consensus will become unstable, okay? So, yes?
One of the top slides, if the single agents are stable, then the network is stable.
Yes, for diffusion.
And if only if?
Sorry?
For diffusion.
No, that's not what I'm showing. I'm showing in one direction, right? That's all I showed. I did not show if and only if, right? What I showed is that if the, no, because you see, okay, because, okay, in general, okay, rho of B of diffusion is less than or equal, right? Not in this case, but in general, that will be the case. So, okay, so this statement is for the general case, okay? Anyway, you get the point, right? So there is no need to pursue this anymore, right? So let's continue, okay? Fine? So these kinds of properties and this kind of derivation to characterize the evolution of the network is what we will be doing in the general case after this lecture, okay? And the same issues will come up, but more generally, okay? Very good. So now that you saw what happens in the mean square error case as an example, let's now go back to the general case, okay? So what was the general problem that we are interested in? We are interested in solving this problem, right? I have a collection of agents. Each one has an individual cost function. There is a topology, coefficients, right? Combination weights. I would like to find the minimum of this global cost, okay? Well, and remember, the global cost is strongly convex, so it has a unique minimum, right? By assumption, it's strongly convex. So the minimum has to satisfy this condition. The gradient is 0 at the minimum, right? So whatever the minimum is, it has to satisfy this condition. The sum of the individual gradients have to be 0, fine? Okay. Okay. Now, in the general case, a few changes are going to happen. First of all, like I mentioned before, okay, the Hessian matrices will not be block diagonal anymore in general, right? Remember I told you when we talked about how to compute Hessian matrices of functions of complex arguments that in the quadratic case it's block diagonal, but in general it's not block diagonal, right? Logistic regression or other functions, more general functions will not be block diagonal, right? So that's one complication. The second complication is that the individual costs may not have all the same minimum, right? The minimum may not be the same, okay? Because of that, some complications are going to happen, okay? Which we are going to address, okay? The first complication that's going to happen, and we'll talk about this later, is that it will not be enough anymore to only examine the evolution of these quantities to determine how the network is evolving over time. This is not sufficient anymore, as it was in the mean square error case. That's all I needed to talk about, right? And then I derived the recursion for W tilde. You are going to see that in the general case, I need to study the evolution of things like this. Let's define an extended vector at node K like this. This is W tilde Ki, W tilde Ki. This is a column, right? If you compute the star of it, it becomes a row. And then the transpose back to a column. This vector has size 2m plus 1. It turns out in the general case, you have to study the evolution of these extended vectors. It's not enough to study the evolution of just this quantity, okay? You are going to see why. Because of the block diagonal structure of the Hessian matrix, you have to extend your individual state vectors into dimension 2m by 1, okay? You have to do it for all variables in your problem, all variables. When the Hessian matrix becomes block diagonal, then this reduces, collapses, okay? You are going to understand this later. I will explain to you why, okay? But the other more important, or the other equally important fact that comes up, which I'm going to talk about now, and the other fact later, is that the network will not be converging to the omega 0 that we want, which is the minimum of the aggregate cost. It will now be converging to something else, W star. That's the star, right, of the show, not this. It will be, this is not conjugate, okay, star, just a star, okay? So it will be converging to something else, which I would like to identify. What is that something? And how do I make that something be equal to omega 0? And why does it converge to that something else, right? These are questions that we need to understand. The coupling will force, okay, the coupling will be a cause for this, okay? So we need to understand what this W star is, okay? So let's get into it. Okay, so here I have the algorithms again. You see, this is the same as before, except that now I'm using the approximate gradient vector in the general case. It's not mean square error anymore, so I'm writing the general approximate gradients here, right? Okay, this is exactly the same recursions as before. I capture them into a single recursion as before, right? Exactly the same thing, right? A1, A0, A2, and you have here the approximate gradient, right? Approximate gradient at where you are. Fine so far? Okay. And these matrices, they are left stochastic, just like before, okay? So you see the analogy, okay? That's why I spent some time on the previous case. We introduced the product of the three matrices, A1, A0, A2, like before. In general, this matrix will just be the A, because two of them will be identity almost always, for the cases you are interested in, okay? We assume that P is primitive, right? So this P plays the role, okay, P is A for the cases we are interested in, so we assume it's primitive. But for the general case, if we have the three A's, it is the product of the A's that we need to be primitive, okay? But for all practical purposes for us, saying that P is primitive is the same thing as saying A is primitive, right? The network is strongly connected, you understand? But just because we are dealing with it in the general case, then we are going to say that P is primitive. Well, if P is primitive, you already know what it means. It means that it has a single eigenvalue at 1, right? P is a left stochastic matrix and primitive. From the Perron-Frobenius theorem, like you know, it has a single eigenvalue at 1. Okay? And it will have a Perron eigenvector, little p, right eigenvector, whose entries are normalized to add up to 1. And all entries are positive, right? The Perron eigenvector of this P matrix. For consensus or diffusion, this is simply the Perron eigenvector of the A matrix, right? If this confuses you, just think of P as the A. It's just because I'm keeping the presentation general to capture many different algorithms at once, okay? Fine? Okay. So I'm trying to tell you what this W star is, okay? Fine. Now that I introduced this vector P, and later you'll understand where this came from, okay? Of course, the way I'm describing it to you, you might ask, how did you guess that it is this way, right? It's because I'm explaining it to you after the fact, right? I already know what the result is, so I'm explaining it to you first. Later you're going to see how this came about, okay? Not in this lecture, probably in the next lecture, okay? So look, P is a vector with positive entries, correct? And A2 is a matrix with non-negative entries, okay? So when you multiply A2 by P, you get a vector with positive entries, okay? Because none of the rows of A are 0. If the rows of A are, right, because this is a connected network and we're assuming none of the rows in these A's are 0, okay? So this is a column, and then you scale them by mu's, fine? So you end up getting a column vector, fine so far? With all entries positive. Let's take an example. Let's assume I'm talking about diffusion. Okay? Let's say ATC diffusion. What is A2? A. What is AP? P. Right? Right? AP is P itself. So Q is simply the entries of P scaled by the step sizes. Correct? Okay. Let's take CTA diffusion. What is A2? Again, you get scaled multiples of P. Right? Consensus. What is A2? Again, you get scaled. So for the cases of interest to us, Q is simply scaled multiples of the P's, right? Right? What you see there is just the general case, right? Fine? Okay, so don't be bothered by this. So Q is simply a scaled multiple of Q's, scaled by the step sizes. And if all the step sizes happen to be the same, the agents are using the same step size, it's just some mu times the P, right? Okay. So this is what we are going to be showing later, okay? Now, remember the step sizes, they are all small numbers. There is one among them that's the largest. Okay, I'm going to call it mu max. This is just notation, okay? You'll see why later. It makes things. And all these tau, and therefore all the mu's will be multiples of that mu max, and these taus are all numbers less than 1, right? It will be 1 for the maximum, right? This is just normalization, right? Okay? All these step sizes are multiples of some maximum value, and these taus are always numbers less than 1, fine? This is just notation, okay? You will see why it's useful later. Okay, so now I'm going to introduce this weighted cost. Weighted cost. How is this different from the original aggregate cost that we are interested in? The Q's were all 1 before, right? Okay. So will this cost have the same minimum as the one without the weights? Not necessarily, right? Not necessarily. If the Q's are not all, if the Q's happen to be all of them equal to each other, right? Then obviously the minimum of this is the minimum of the original cost. But in general, that's not the case. Can you give me an example of a network where all these Q's will be equal to each other? So let's take diffusion or consensus. Then the Q's are multiple of the P's, right? Let's assume all the mu's are the same. And when would all the P's be the same? Doubly stochastic. For a doubly stochastic case, right? So that's a situation. If you have a network where all agents are using the same step size and a doubly stochastic A, right? Then omega 0 and omega star will be the same. Omega star is the minimum of this, right? So if your network is using a doubly stochastic A, this issue, and constant step size, uniform step size, this issue of differences in the location of the minima doesn't come up. Understood? Okay, so that's one situation, okay, when all the Q's are the same, okay. So this is just to show you that if the original cost is strongly convex, this new cost, weighted cost, is also strongly convex. Why? Compute its Haitian. Here it is the sum of the individual Haitians. Obviously, if I replace the Q by the smallest, this is larger than that. This is lower bounded from below, so this whole thing will be lower bounded from below. So if this has a unique minimum, that has a unique minimum. I call the unique minimum of this omega 0. I call the unique minimum of that omega star. Okay? Here it is. The minimum of that is omega star. Okay? This is just repeating, right? We are interested in solving the top problem, finding the omega 0 that satisfies this. I claim that these networks in general, of course, if you are not under a doubly stochastic A or uniform step sizes, this issue doesn't come up. But in general, more generally, if these Q's are not uniform, you are actually converging to this minimum. And then I'm going to give you examples how to make them the same, and I'm going to give you examples about how this can be useful as well, okay? Can you give me another example where omega star and omega 0 would be the same? You gave me one when A is doubly stochastic. Another example. When all the individual costs happen to have the same minimum. For example, MSE. Because if all of them happen to have the same minimum omega 0, that omega 0 has to be a minimum for this cost, regardless of the Q's. Right? So that's why for the MSC, this is not an issue. Okay, because if the costs happen to have the same minimum. So there are many situations where these two minima are the same, but not always. Okay. Okay. These are the two cases you already gave me, okay? Doubly stochastic, and when the individual costs are minimized at the same location. These are two examples where W star and WO will be the same, okay? Of course, I'm claiming that the network will be converging to this W star, but I haven't proved it. That's what we will be doing in the next lecture, okay? In the next lecture, I will be showing that if I now measure the errors not relative to omega O, but relative to omega star, right? So now whenever I write an error, I mean omega star. And then your situation will determine whether that omega star is omega 0 or not, right? We'll show in the next lecture that the size of the mean-square error relative to omega star is very small, of the order of the step size. Usually we now write of the order of the largest step size, but this step size is small, right? Okay. So this is essentially this result. Once we prove it in the next lecture, we would have proved that the network is approaching actually W star, okay? Right, so this is the, I'm only stating this theorem, right? That's theorem in chapter 9. I'm stating it. We'll be proving it in the next lecture, right? We are going to show that all the agents in the network are going to approach this omega star in this sense, okay? The mean square error will at most be of the order of mu max, okay? Which would, this would essentially correspond to saying that the network is mean square stable, okay? And we know that it converges in the mean square sense to that point, okay?
What about the mean of the error?
We will be talking about it in chapter 9. I will also give you, remember I did it for the single agent case. I gave you 3 lim sub bounds. One for the mean square, one for the absolute value of the mean, one for the 4th order mean. I gave you mu, and mu squared. The same thing will hold for the network, but relative to omega star. So that's one of the results we'll be proving later, okay? Everything we proved in the single agent case will extend, but with some effort. For example, this issue that of omega star and omega 0, you didn't have it before, right? Okay, so let's continue. I will explain to you what this omega star means very soon, okay? But for now, I'm just stating the results that we'll be proving. Now, this is just a convenient normalization. You see, if I take each Q, remember the Q's multiples of P's, right? In the general case, they are multiples of A2P, right? Okay. I can normalize each one of them by dividing by the sum and define instead this normalized global cost, right? With Q bar here. How does the minimum of this, the minimizer of this, compare to the minimizer with the original Q's? They are the same. They did not change, right? So why do I normalize? Okay, just for convenience, and you are going to see this in a later lecture. Why for convenience? If all the J's happen to be the same, what would be the value of this normalized global cost? Would be that cost, right? Because the sum of the Q bar is 1. In the previous case, when I didn't normalize, it will be J times some number, right? So even though they have the same minimum, but they don't have the same value, apart from scaling, right? So in some studies that we will do later, it would be important for us to know that this function that we are minimizing has the same minimum and the same value. Okay, so this is just a small detail, okay, nothing deep here, okay? I'm just introducing it at this stage because this is the right place to introduce it, okay? Very good. Well, you already answered this, that if I'm talking about consensus or diffusion, then 2 of the A's will be identity, 1 of the A's will be A, right? And therefore the Q's will be this, right? We already handled this before, right? I asked you this question and you already answered it. Okay. Since the Q's will be this, so even if your matrix is doubly stochastic, it doesn't necessarily mean that the network is going to go to omega 0. Why? Because you still have the mu's here, right? Unless the mu's are uniform, right? So, which I wrote as mu times tau, okay? Mu times tau. Right? So even if your combination policy is doubly stochastic, it doesn't mean that the network is going to go to the omega 0, unless the mu's are uniform as well, right? This is, okay? What I'm trying to say, it's not difficult to see that in general the network is going to go to some W star, not omega 0, okay? Very good. Okay, so what is this omega star? What is the interpretation of this omega star? Okay, so let me explain it to you. Okay. So what I did so far, I just defined what omega star is. It is the minimum of some weighted cost. And I told you what those weights are. How did I guess that? You'll understand it next time, okay? I'm just stating the result, and the proof is next time. So now let me explain what this omega star means. Okay. Now remember, you have several cost functions, one associated with each agent, right? And each one of them has a minimum, right? Each one of them has a minimum. So now you have a collection of agents. Each one of them has a utility function or a cost function. And you would like them to work together, right? To solve some problem of common interest. So where should they converge? You would like them to converge to something of common interest, right? You would like them to converge to some location of common interest. So one way to define this location is called Pareto optimality, okay? Pareto optimality. So what's that? Let me define it first and then show you some examples. Okay? So definition first and then I'll explain, okay? So a solution, some solution W star is said to be Pareto optimal, right? If, for all agents, for the n agents, if there doesn't exist any other solution, I'm calling it W. This is bullet, right, using the LaTeX notation for it, right? There doesn't exist any other vector that dominates it. What does this mean? Okay, this means the following. Okay, technically this means the following. Assume that your agents converge to a Pareto solution omega star. Then you cannot find any other solution. It means that you cannot find another solution such that it will improve at least one of them. It doesn't degrade the others. If you can find another solution, right? If you can find another solution that at least improves one of them, strictly improves one of them, and does not degrade the others, right? The cost is less than or equal, this would be a better place to be, right? From the perspective of all of this multi-objective optimization problem, right? Each one has a cost function. From the perspective of all of these agents, it may be better to be at this location than at that location because the W bullet, if it satisfies these conditions, it dominates omega star, okay? It improves at least one, doesn't degrade the others, okay? So a Pareto solution is one where you cannot find such a W star. You cannot find another solution that will dominate W star. Then you call it a Pareto solution, okay? And Pareto solutions are not unique, as you are going to see, okay? I'll show you an example, a graph, okay? So, for cooperative agents, this is a good notion, okay? This is a good notion because if the agents are cooperative, they have the common good in mind. It's not always the case that networks and agents over networks have the common good in mind, right? I'm talking about cooperative networks. If you have malicious agents, they can cause other kinds of problems, okay? But if they are cooperative agents, K0 will not feel like moving to this place because, right, it is encouraged to move to that place. Its cost would be better because it knows if I move to this place, I am at a Pareto solution. If I move to this place, I'm going to affect somebody else. Somebody else is going to see degradation in performance, right? So once the network converges to a Pareto solution, the agents will not feel like moving away from it because they are going to hurt somebody else. You understand the concept? Okay, so let's look at a graph so that you understand it better, okay? Here I'm just repeating the definition. So W star is Pareto optimal if you cannot find another solution that dominates it. Like that, okay? So this is, and again, so in a cooperative network, no agent will feel like moving away from its Pareto solution because it's going to degrade the performance of somebody else, okay? So let's look at this graph so that you understand it. So let's take the case only of two agents. I have two agents. This has a cost, and this has a cost, or a utility function, or a risk function. Okay. Let's first consider the case where both costs have the same minimum. Okay, the same minimizer. Okay. So what I am plotting here, okay, so this is the first cost, this is the second cost. I'm plotting them against each other. So if you pick any point in this space, if you pick a point here, it tells you what the value of J1 of omega is, what the value of J2 of omega is for that particular value of omega, whatever value it is, right? So what is the smallest value that J1 of omega can achieve? It is here, right? That's the smallest value J1 of omega can achieve. Okay, this, you see, J1 of omega is increasing in this direction, right? So the smallest value that's possible for it is here. And the smallest value for J1, J2 is here. So this is the case where both costs have a common minimizer, right? A common minimizer, and both of them reach their minimum at the same location, and that will be the global minimum, right? Let's take another situation now, the one on the right. Okay, the one on the right. Where is the smallest value that J1 of omega can achieve? At S1, correct? This is the smallest value. Where is the smallest value that J2 of omega can achieve? S2, right? So these are different now, right? So different, okay. Now, assume that the network is at some location here. Okay, is at some location here. The omega happens to be such that J1 of omega is here, J2 of omega is there. Okay? Can we change this omega in order to improve the performance of the network? Okay, can you do that? For example, if this moves to the left, which cost will be improving? J1 will be improving. What about J2? It remains the same, right? Okay. So if you go in this direction, okay, so J1 will be improving and J2 will be the same, right? If you go down in this direction, J2 will be improving and J1 will be, in this particular case, J1 will become worse, right? Oh, you mean vertical? You are looking at this as vertical? Okay. I'm just moving randomly in that area, okay? It's not vertical, neither horizontal, okay. Now, let's take another example. Take a point on the curve, on this blue curve, B, on this blue curve B, okay? I claim that all points on this blue curve are Pareto solution. Okay, by that I mean you don't feel like moving away from it without degrading the performance of somebody, right? You saw here I could move with, I did not degrade the performance of anyone. I improved one, I did not degrade the other, right? But let's take point B, okay? Point B, if you want to improve the performance of J1, you have to move away from the valid space, right? The feasible space, so that's not possible, okay? It's not possible to move to the left, okay? If you move to the right, what will happen? J1 will get worse, okay? If you move down, what will happen on the blue curve? If you move down on the blue curve, J1 will get bad, will get worse, right? If you move up, right, so once you are there, you are there, okay? If you move away from it, somebody is going to be hit, right? Even though you may improve your performance, somebody is going to be hit, right? So all points on this blue curve, okay, are Pareto solutions. Okay, once you are there, you cannot find another solution that dominates it, right? Okay, so this is one illustration, okay? So this text is just explaining that. I have an animation here to explain it in another way, okay? To explain it in another way. I have two costs, two agents, K and L. Each one has a quadratic cost at it, okay? And on purpose, the minima occur at two different locations, fine? At two different locations. The sum of these two costs is also quadratic, right? The sum of two quadratics is also quadratic, right? I'm not going to draw here, okay, maybe you can imagine, right? The sum of these two will be some quadratic with some global minimum, right? Which is not necessary, which doesn't agree with the individual minimum. Okay, fine. So now, I claim all the points in between these local minima are Pareto optimal solutions in this case. They are the Pareto optimal solutions, meaning that this network of two agents, you can make it converge to any point in between. Okay, because I showed you before, if you run consensus or you run diffusion, you're going to converge to a Pareto optimal solution. I'm claiming in this case that the Pareto solutions are all points in between these two local minima. I'm going to show it to you analytically, okay? So how do you see that? For example, let's run this simulation. These are the two agents, right? They are moving, right? And they converge to this point. They converge to this W star. This W star is a Pareto solution. Why? Let's look at it why. Let's assume that the blue agent decides to improve its cost. It will have to move in what direction? To the left. If you move to the left, what happens to the yellow cost? Gets worse, so it will not do it. If this tries to move to the right, this guy gets hit, right? So once it converges to a point, that point is a Pareto solution. Neither one of them will feel like moving away from it. They could have converged to another Pareto solution, but once they are there, they don't feel like moving away from it because somebody else is going to be hit, right? Okay? And I claim the network can converge to any one of these Pareto solutions, okay? So how is that? You understand now what Pareto solution means, okay? It's a point. Once you are there, none of the agents feels like moving away from it. Okay, they all have individual minima, right? And the Pareto solution is one way to get them to work together to go to a common place where none of them will feel like moving away from it. Okay, that's in a cooperative network. Okay, now, how do you find Pareto solutions? So this is independent of the network question. How do you find Pareto solutions? If I give you a collection of costs, how do you find all Pareto solutions that are associated with that cost, with this collection of costs, okay? You use a scalarization procedure, okay? Technique. This is what you do. Pick any non-negative numbers pi sub k, okay? And find the minimum of this aggregate sum. Then you can show, I'm not showing it here, right? You can give references, but you can show. For any choice of a collection of weights pi k here, for each choice you get a Pareto solution. That's how you find it. You have to minimize a weighted sum. You are free to choose the pi's. So for each choice of the pi's you pick, you get a Pareto solution. Now, what are we doing? I claim that my network is converging to the minimum of this. That's why this W star that we are converging to, right, is one Pareto solution. That one that corresponds to this choice of the pi's. Okay? So this is one way to find Pareto solutions. Pick weights pi, okay, and find the minimum of that. That gives you a Pareto solution as a function of the pi's, right? For different pi's, different Pareto solutions, okay? That's exactly what I claim the network is doing. It's finding this particular minimum, which happens to be a Pareto solution corresponding to this Q, correct? Okay? Yes.
Should all the Pareto solutions be continuous in the
Yeah, that's a good question. For the yes, for the functions that we are dealing with here, you will get this kind of behavior that we see here. Okay, you'll get curves like this. Okay, like this, and people call it the trade-off curve. Okay, you will get curves like this. In the case when they are the minima are collocated, you get a unique minimum. But in general, you are going to get a trade-off curve like this, where you have infinitely many Pareto solutions sitting on it. Okay. Of course, this is a 2D curve, right? In higher dimensions, you will have surfaces, right, and higher dimensional spaces. Okay? Here, surface. okay, for higher dimensions. Let's do examples now, okay, examples. Assume I have a network with mean square error costs. Fine? Here, mean square error costs. I'm not assuming now that the minima are the same. I did not tell you that D is UW plus V, because once I tell you that, that forces the minima to be the same. I'm just giving you costs with different RUKs, RDUKs. These are quadratic costs. The individual minima are here, okay? How do you find all the Pareto solutions for this problem? Okay? You do this. You find the minima of this combination for non-negative pi's, right? How do you find the minimum of that? Gradient equal to 0 and solve, right? And the gradient of quadratic cost is simple, right? Is linear in omega, right? Okay, so this algebra can be done in closed form in this case, okay? That's exactly what I did, okay? Compute the gradient of that sum, put it equal to 0, you find this expression. You see the pi's are here. You understand where this came from? Okay, so this is the expression for all Pareto solutions as a function of pi, okay? Now, remember that WKO satisfies the normal equations, right? Always. So I can replace this RDUK by that, right? Okay, so if you do this, you will get here pi k RUK, and here you have pi k RUK. So here you have the sum of the inverse, pi k RUK times WK0. So what's the conclusion? The conclusion that all Pareto solutions to this problem consisting of quadratic costs are given as convex combinations, right? Convex combinations of all of the individual costs, okay? Because these B's add up to 1 and they are non-negative matrices. You understand? So here we were able to, I gave you the example of two costs and the segment in between. This proves it more generally for multiple costs, m-dimensional vectors, that indeed all convex combinations of these minimum costs, right? So this describes that surface that we were talking about, the curve, the trade-off curve that we were talking about. Okay, you will get it like this, okay? Okay. This is just a simple example, right? When n is 2, when I have two agents, the combination weights will be given like this, okay? So just a convex combination, okay? Okay, so this is for the case of MSE networks. What would be, okay? This is a similar problem, MSE networks, but where the WKs are different across the agents, okay? It doesn't matter, you get a similar conclusion because the individual minimizers satisfy the normal equation, right? The same normal equation, okay? And then you can compute the solution to this expression, the sum of the gradients at omega pi should be 0, right? Just do the calculation. I know what the gradients in this case are. Here they are. Okay, put it here, equal to 0. You again find what the Pareto solutions are. What I'm trying to say, in many cases you can solve explicitly for the Pareto solutions, right? Because all you have to do is find the solution to this equation, right? If the gradient is simple, in this case it is simple because it's linear, then you can find exactly what the Pareto solution is. In general, you cannot. The network can find it for you, right? This is what the results will be showing. If you want to find Pareto solutions for a collection of individual costs, if you can solve it, fine, solve it. If you cannot solve it, the network will give you the Pareto solution, okay? Or at least one of them corresponding to the Qs, okay? Very good. So this is just specializing to the consensus and diffusion case. Okay, I already talked about this a few times. In this case, when two of the A's are identity, then P is the Perron eigenvector of A, the Q's are multiples of P, and then if you plug back into the equation we just found to find the Pareto solutions, this is simply the equation, right? This is simply the previous two equations specialized to this case, okay? So the bottom line of these three examples, if you have quadratic functions, you can solve for the Pareto solution explicitly, right? This is what these three examples are showing. Okay? Here it is. This is the expression for the Pareto solution, okay? Because these are the Q's, right? Or the pi's that the network gives you. Okay? Now I have a simulation to illustrate that this is indeed the case. That the network is indeed going to W star, not WO. Not, okay? So to show it, let's say this is a case here where I'm using this is the uniform rule. Every agent counts how many neighbors I have and I give them 1 over the number of neighbors as weights. This is called the uniform rule, okay? The uniform combination policy. The interesting thing is that, okay, uniform step size. For this combination policy, you can prove that the entries of the Perron eigenvector are given by this expression. This is not difficult to show. We'll be showing it in a future lemma. Okay, what is this? Okay, so I have an A, which is the uniform combination policy. Then P will have, for agent 1, it will be how many neighbors I have divided by the total number of neighbors in the network. For each one, that's what it will be. Okay, so the entry of P is proportional to the number of neighbors. Okay. So since I know P, since I know mu, I can find the pi's, I can find W star, and then I can compare where the network is going in comparison to W star. So this is a random simulation for a network with 20 agents, okay? And this is the regression power, noise power across agents, 20 agents, randomly selected. This is the simulator selects this randomly. And then you run this network, you run diffusion or consensus over this network to estimate, to see where it converges, and you get curves like this. Okay, so this is the learning curve relative to omega star, not relative to omega 0. Relative to omega 0, it will not get close to the theoretical value. I didn't show you yet where it's going to converge to. This we are going to see later. We are in chapter 8. This is chapter 11, okay? But this is just to show you that indeed, the network is converging towards omega star and not omega 0, okay? Of course, I'm going to prove this analytically later. For now, I'm just illustrating it, okay? This is no proof. This is just an illustration, okay? So that's what that curve was about. This is just explaining the example. Okay. So now I come to 2 important points, okay? 2 important points. So I have a network, a strongly connected network, and I showed you that it converges to a Pareto solution, right? To an omega star. What are the weights of this Pareto solution? The Q sub k, correct? And these Q sub k are determined by what? By the P's. And the P is determined by what? By the topology, right? That's what you have to understand. So you see that the topology is determining where you are going to go. Because the A determines P, which determines the Q's, right? Okay. Now, if you have, just to make some remarks, assume all the step sizes are the same. So now, by the way, with these results, you can start comparing networks. Assume all the step sizes are the same. The agents are all similarly equipped, right? Same step sizes. Assume A is doubly stochastic. Okay? I showed you the metropolis rule is doubly stochastic, okay? Okay, I have 100 agents here, the same agents here, the same agents there. You choose any arbitrary doubly stochastic matrix and topology, and you connect them. He chooses another doubly stochastic matrix and topology here, and the third one there. Where will these agents, these networks converge to? all of them will converge to the same point. Because for all of them, the P's are the same, the Q's are the same, right? Regardless of the topology, they will all converge to the same point. But the minute you change, for example, the step sizes, they will start converging to different Pareto solutions, right? Because the Q's will change, right? If the A's are not doubly stochastic, are left stochastic, they will be converging to different Pareto solutions, right? These are Pareto solutions for the same cost functions that we are talking about, the same collection of cost functions, but different topologies depending on the P's, on the step sizes, can guide the network to a different Pareto solution. You get the point? Okay. Now comes the other question. Fine, but what if I want the network to go to a particular solution, right? Okay? Very good. So let's assume, okay? Let's assume, so this, I will show you two ways to do that. Two ways to do that, okay? I just showed you that the network is going to go to a Pareto solution that's determined by these coefficients, right? The minimizer of this weighted sum, correct? So these coefficients determine the location of the Pareto solution. Now, what if I want my network to converge to a particular minimum? For example, I want it to converge to the solution of this weighted sum for some qk primes that I set, right? Assume I want that. How can you guarantee that? Okay, so I will show you two ways. One way is this. If, okay, I'm going to discuss two ways, okay? I have the topology and I'm free to choose A. The topology is fixed, the edges are already fixed, but I'm free to put weights on the edges, right? So what I'm going to do, I'm going to put weights. You give me the qk primes, right? You give me, I want these particular weights, this particular Pareto solution. In particular, the qk primes could all be equal to 1, in which case you want me to go to omega 0, right? So you give me the q primes, and you tell me this is the topology I want you to make to converge to that point. So one way to do it is, I'm going to pick an A such that the P of that A is such that if I multiply them by mu, I get the q prime. Or I get alpha q prime for some constant alpha. It doesn't matter, right? If it is q prime or alpha q prime for some constant alpha, it doesn't matter. So the question now becomes, how do I design an A such that if you find its P and you multiply by mu, you get the q prime, right? Too difficult? Okay. So this is the A. Of course, it requires proof. Okay, I'm going to prove this later, not now. Okay, this is a lemma in the text, lemma 12, chapter 12. Okay, but for now I'm stating it. You can prove it on your own. The proof actually is not difficult. You can prove the following. You give me the q primes, fine? I tell you define this matrix. Build your matrix like this. How? For example, for your neighbor L, you assign this weight, the step size that I'm using divided by the q, and the maximum of these two numbers, okay? Depend on quantities between us, fine? Okay, so this is for every agent in your neighborhood. You assign that weight, and then you add them up, and you make sure they add up to 1. That's what this is doing, the second line. If you build your A like this, okay, that lemma that we are going to show later, or you can do this algebra, you can show that the Perron eigenvector of this A, by the way, this n, like I said always, is the degree of your node, how many neighbors you have, okay? You can show that the Perron eigenvector for this A has these entries. It is a multiple of the qk prime. And this is a constant thing, okay? Sorry, you can show that mu k times p, that's what we want. Mu k times p is a multiple of qk prime. And this multiple is a constant for all agents because it's adding over all agents. This is some alpha, right? That's called the Hastings matrix, by the way, Hastings matrix, okay? You see, so I answered the first question, right? Now, how do I show that the P's of this matrix? You can do it. This is simple algebra. We are going to do it later, okay, in a future lecture. But if you are interested in checking, you can check. You understand? So this is one way to do it. But in this way of doing it, the network is given. I only have the freedom of changing the A's. Fine? Okay. That's one way. In particular, if all your Q's are equal, right, because you want to go to omega 0, which A should you pick? Well, if all the Q's are equal, they will disappear, right? Pick that A. They disappeared, right? If you pick this A, your network will go to the omega 0 that you want, right? Okay. If all of the step sizes are equal, then this will disappear, right? And this becomes the metropolis rule, which is doubly stochastic. It will also go to omega 0, right? This is metropolis rule, okay? You understand? So even though your network is going to W star, you have some control over it, right? But you know now which part to control, okay? The other example I want to show you, what if you give me the network, the topology is there, and you gave me an A and you tell me don't touch the A, right? So I cannot touch the A now. The network is given, the A is given, but I want it to go to this place. So how do you do it? Okay? So how did I solve the first problem? I picked an A to make this quantity equal to the Q you gave me, right? Well, now you are also giving me a Q, okay? You are giving me a Q, or let's say here you want it to go to omega 0. You can make it more general, but in this example I'm showing it to omega 0. What I do, I make this product equal to a constant. I know the A. I have the A. So I know in principle, I know the P's, right? So I adjust the step sizes across the agents such that the product mu P is always a constant, right? If that's the case, the Q's will be uniform. You will go to omega 0. If you want different Q's, you adjust them to be equal to these different Q's. You understand? So here I did not touch the A. However, to implement this solution, you need to know the P for that A in a distributed manner, right? Of course, if I have the A here, you can put it into MATLAB and find the P, right? But I need to find this P, the Perron eigenvector, in a distributed manner. Well, in some cases, you already know what this P is in closed form. For example, if your A happens to be uniform combination rule, I already showed you what the P's are. The degree is the average, right, by the total degree across the network. So in many cases we know, in some cases we know exactly what the P's are beforehand. If you tell me what type of network, for example, if it's doubly stochastic, right, in some cases I already know what the P is beforehand. So you just put it there and pick the mu. If you don't know what P is, okay, if you don't know what P is, then you can run a power iteration. You know what a power iteration is? Assume you want to find, I have a matrix A. This matrix A has largest eigenvalue, 1. All other eigenvalues are strictly less than 1, right? The power iteration, you start with a random vector, and you keep multiplying it by A repeatedly. A times A times A, right? Then the power iteration, you can show that this repeated product makes this R converge to a multiple of the largest of the eigenvector corresponding to the largest eigenvalue, which is P. So if you run this iteration repeatedly, this R is going to converge to a multiple of P. That's where you can read the P from. And that's what I have here. You see? So every node K, okay, because it is A times R. So every node K, okay, has access to a column of A. Okay, here we're assuming it has access to the column of A and to the row of A that correspond to it. Okay, so every agent runs an inner product, one part of that multiplication. This is row times column, and another agent runs another row times column. So every agent runs a recursion like this, and this RK with time should go to a multiple of P. That's the idea, okay? You get it? So mu is mu 0 over that, okay? Okay? So do you have any questions?
So
Yes.
in this model, we are assuming that each node is having different W zeros.
Yeah, this is a general case, yeah. Yes.
And we can make each node go to its own minimum.
No. I'm talking about the network. I want the network to go to W star. Okay, it's going to approach this W star in the mean square error sense. It's not going to converge almost surely, right? So each node is going to fluctuate around omega star.
So can we enable somehow each different nodes to go to their own minimum?
Yeah, that's a different kind of problem. You can study problems like that, and you have studied problems like that, okay? But that's not what I'm talking about here, okay? If you are interested, I can give you some references on that, okay? But that's a good question, but it's a different context than this. Yeah. Fine. So today what I did, I'm going to stop here today. What I did, I showed you how do you examine the evolution of the error vector over the network. I illustrated that for mean square error networks, right? And I showed you that when I consider the general case, which I will do next time, right, I have to extend this analysis. I have to extend the error vectors. I have to introduce Hessian matrices that are not block diagonal. So the equations will look a little bit different, not much different, but a little bit different. And then I went to the next point. Fine, this is how the error evolves, but tell me now where it goes to. Right? So I told you that in the general case, the network is going to go to a Pareto solution, omega star. And I told you what determines the Pareto solution are these coefficients Q sub k, which come from the P's, which come from the topology. So just remember in your mind where I'm going to depends on the topology. Right? That's essentially what this is. In what way? Then the expressions tell you exactly in what way. And then towards the end, I explained to you two ways by which you can make the network converge to points of interest, right? To particular Pareto solution or to the global minimizer. Fine? Okay. So starting from the next lecture, I need, of course, to establish now these various statements that I gave you. So that's what you are going to see. So the next 2 or 3 lectures will be the most demanding in this course. Okay, because that's where we are going to establish these properties and study the evolution of networks very clearly and very analytically, okay, so that all these statements are proven, okay? After that, it becomes easier, okay? But for the next 2 or 3 lectures, you'll need to be a little bit patient, okay?